All right, ladies and gentlemen, welcome back. Happy section 4.1 day 1. Today we're talking about extreme values of functions. So here we go. So today we're going to start with absolute extreme values. So right off the bat, real quick, absolute extreme values can also be called global extreme values. Okay, so let's get into what these are. So an extreme value is basically going to be a maximum or a minimum. So these are terms you may recognize from Algebra 2, hopefully, when you talked about functions. You may have learned about these. So let's get a little more in depth on the types of extreme values we're going to be looking at. Let's start with a function f that has a domain that we'll call D. So whatever that domain is, whatever that set of numbers is, we will refer to it as D. Then f of c, now a lot of letters here, so we should establish right away that c is an element of the domain. I always mess that up. I think it's like this actually. So I think this is notation we've seen before, right? That E there is supposed to mean an element of. So C is some, X value in the domain of this function. So an absolute maximum value, so f of C is an absolute maximum value over the domain of this function if, and we use the misspelling IFF to mean if and only if, f of x is less than or equal to f of c for all x values in the domain. So let's slow that down for a second. Okay, so what are we saying here? F of c. F of c is the output of a function, right? Because we've taken c, plugged it into the function, now we have an output. That output is the absolute maximum value if and only if all of the other outputs are less than or equal to the output we started with, which is f of c. So that's an absolute maximum value. So now what we're going to do is we're going to take this definition and we can go ahead and get a little copy and paste going. And we just have to flip a couple of things around here. An absolute minimum value. So f of c, again, this is the output of a function. We can call this an absolute minimum value on the domain if and only if all of the other outputs, f of x, are going to be greater than or equal to f of c. So again, f of c is the minimum value if all of the other outputs are greater than or equal to it. F of c is a maximum value if all of the other outputs are less than or equal to it. So again, both of these fall within the category of absolute extreme values. Okay, so this is the absolute biggest output the function can give us. That's the absolute max, or the absolute min is the smallest output that we can get from this function. Let's take a look at an example. So example 1, we have to start with the domain. Domain is very important in this section. Bracket negative pi over 2 to pi over 2. So some radian here for my domain. And let's look at two functions. So let's first start off with cosine of x. And what we'll do is, on the left here, we'll do a little graph of what cosine looks like. So I'm going to zoom in here. So let's start with cosine of 0. So cosine starts at the top of the roller coaster. And then cosine of pi over 2 is 0. And then cosine of negative pi over 2 is also 0. So looking at cosine from negative pi over 2 to pi over 2, we get something like that. Okay, and now let's identify the absolute maximum value. So absolute maximum value, what is the biggest output that occurs for this function? So the biggest output we can get for cosine the biggest output, the biggest y value is going to occur at the top right there, right? That's the biggest output we can get. So the absolute maximum for cosine on that domain is going to be, whoops, wrong tool, is going to be +1. Again, output. So we want to say the y coordinate here, right? It occurs when x is 0, but the absolute maximum value is 1. Let's talk about the absolute minimum value. So what's the smallest y coordinate we get for cosine? Now, if we think about just, hey, what's the range of the cosine function, we would say -1 to 1. But the answer for the absolute minimum here is not -1, right? That would be over the entire domain of cosine of x. That's not what we're looking at here. This is only from -π/2 to π/2, right? And so now we see that the smallest y we get is 0 at -π/2, and it also happens at π/2. So the absolute minimum value is going to be 0. Let's do the same thing for sine of x. So sine of x, let's start with a graph. So I'm going to come back in here. Sine of 0 is 0. Sine of π/2 is 1. Sine of -π/2 is -1. And my sine graph looks like that. Kind of. And now, same thing. Let's identify the absolute max and the absolute minimum for sine. So, looking at this graph, the absolute maximum for sine occurs at π/2, and that absolute maximum is 1. And the absolute minimum occurs at -π/2, and it's -1. Okay. So, again, absolute maximum, what's the biggest output we get for the function? Absolute minimum, what's the smallest output we get from that function? And we have to pay attention to what the domain is. For sine, -π/2 to π/2 encompass the entire range, right? So we got 1 and -1, but for cosine it did not, right? So we did not get -1 as one of our answers there. Okay, let's talk a little bit more about domain. So we're going to take a look at a pretty simple function, y equals x squared. And before we get too into this, just a real quick Latin lesson, because I know you guys come to me for all your Latin needs. Absolute extrema on the domain. So extrema, fun fact, is the plural form in Latin of the word extremum. Okay, so an individual max or min is called an extremum. The plural is called extrema. You do not need to know that for quiz, test, or really anything, unless you decide to take Latin, which would be kind of cool, but not going to be quizzed or tested on that. Just something kind of fun. Okay, anyways, back to y equals x squared. So basic parabola here, right? We're going to take a look at it over a bunch of different domains, okay? Let's start off with the domain of the function itself, which is all real numbers. And so just a quick little sketch, we know what y equals x squared looks like. And now, what is the absolute maximum value? So if I think about this parabola, right, what do the arrows indicate, right? The arrows indicate that this graph is going to go up forever. Okay, well, if it goes up forever, then I think it's safe to say the absolute maximum would be infinity then, right? Unfortunately, that is wrong. Okay, I'm going to scroll back up real quick. This is called absolute maximum and minimum value. These are extreme values. Values, values, values is a key here, right? Infinity is not a value. Infinity is not a number, right? We do not have an absolute maximum value because this graph goes up forever. So, whatever you think could be the biggest y value when you graph y equals x squared, whatever that number is, I can always just add 1 to it and get a bigger maximum value, right? Or I don't even have to add 1. I can add 0.001, right? I can add something just so minuscule, and I can increase that maximum value. And if you do that to whatever I say is the maximum value, then I'll do that to whatever you say is the maximum value, and we'll keep on doing this until, the end of time. So, long story short, right, this graph is going to go up forever, so there is no single absolute maximum value here, okay? Let's talk about minimum value. So if I look at my graph, right, over its entire domain, its absolute minimum value is 0, which occurs at x equals 0. So the answer is 0. Now, if you want, you can start doing this, and I won't take off for it. You can throw in the x coordinate as well. It's kind of like writing an ordered pair, but backwards, right? The minimum value is 0, and then where it occurs is the x coordinate. So that's not necessary, but it doesn't hurt either, okay? Okay, so that's over the entire domain of x squared. And these answers make sense, right? There is no max. It goes up forever, right? X squared cannot be negative. The smallest we can get from x squared is 0, right? So everything makes sense so far. Okay, let's change up the domain. Let's go bracket 0 to 2, okay? So we're looking at a tiny piece of this parabola. Same questions. What is the absolute maximum value? If I'm looking at this parabola from bracket 0 to bracket 2, the maximum is going to occur when x is equal to 2, right? And that maximum value is 2 squared, which is 4. And if you want to write comma x equals 2, you can, but you don't have to. But you can. Doesn't matter. Okay, minimum value. So what's the smallest this is going to be? So the smallest is going to be at 0, and that output is again going to be 0. Okay, so that one's not too bad. Let's switch up the domain again. Parentheses 0 to 2 bracket. Now, this is where we start, letting things get a little bit interesting. Okay, so bracket 0 to 2 bracket, that's a closed interval, right? We have a starting point, we have an ending point. But what if we don't have a starting point? What if we just have the ending point at 2? How is that going to affect the graph? So we put an open circle at 0, 0, right? And then I still end at a closed dot up and to the right. So the absolute maximum value is still going to be 4 at x equals 2. But what's my absolute minimum going to be now, right? What's the smallest y value that is included, right? It has to be part of the function based on the domain that we have. So parentheses 0, right? 0 squared is 0, right? That point is not included here, and so there is no minimum. Whatever you think is the smallest y number you can think of, right? So whatever you can think of, 0.000001, right? Well, I can just go ahead and put another couple of zeros before we get to that 1, and now I have a number that's smaller than yours. And we can keep on getting smaller and smaller and smaller and smaller and closer to 0 without ever actually equaling it, right? And so there is no absolute minimum value here. Okay, last domain that we should look at, parentheses 0 to 2, right? And so now I'm starting and ending with open circles, and so that gives me no absolute maximum value, and it gives me no absolute minimum value. So clearly, domain can have a big effect when you're talking about maxes and mins, and that brings us to our next topic, our first theorem of the chapter, the extreme value theorem. This is a theorem that I kind of like to think of as the money back guarantee theorem. So I'll put a little $ here, money back guarantee. Okay, so here's what it says. If f is continuous on a closed interval, which we'll call a to b, so that'll be our domain, so bracket a to b, so starting and ending at an endpoint. If your function f is continuous on a closed interval, so right there, if you meet both of those conditions, here is the guarantee. The guarantee then is that f has both an absolute max and absolute minimum value over that interval. Okay, so again, this theorem is not saying that in order to have an absolute max and a min, you must have a continuous function on a closed interval. It says if you meet those requirements, then the max and min are guaranteed or your money back. Okay, so what can that look like? So that can look something like this, where the endpoints are the max and the min. So looking at this picture, right, we have the the max over here at A, and we have the min over here at B at my two endpoints. Or it could look something like this, where we have the minimum somewhere in the middle of the interval, and then the maximum could be either of the endpoints. You know, you could flip this picture around and it would still have an absolute max and min. Or it could look something like this, where the absolute max and min are just both somewhere in the middle of the interval. Okay? But again, all this does is that it guarantees a max and min if you meet both of these requirements. Okay, continuous on a closed interval. Okay, so if you're doing a question, and which we will later on, where it says find the max and min, find the absolute max and min of this function, right? You can tell a lot about the type of answers you're going to get if you can figure out, hey, is this function continuous? And hey, are we looking at it on a closed interval, right? So for example, you know, if I said find the max and min of y equals x squared on the interval parentheses 0 to 2 parentheses, yes, I know x squared is continuous, but if it's not on a completely closed interval, then it's not guaranteed to have both a max or a min. The only one that had that, right, was bracket 0 to 2. Okay, and this brings us to my next point, which is that, again, this is not saying the only way to get an absolute max and min is to be continuous on a closed interval. Let me show you an example of that. So let's say this graph here is my function f of x. Okay, this graph clearly not continuous. This graph also clearly not on a closed interval, right? A lot of gaps here. There is no function here between a and b. There is no function here between c and d. But does this graph have an absolute max and an absolute min? Yes, it does. The absolute maximum occurs where? Right here at x equals a. That is the absolute maximum value up there. Absolute minimum value, is it at 0? Nope. It's actually over here at this point D. That's my absolute minimum value. So, is this graph continuous? No. Is it on a closed interval? No. Does it have an absolute max and min? Yes, it does. Okay. The extreme value theorem again, right? This is super critical with this. It's not saying the only way to have an absolute max and absolute min is to be continuous on a closed interval. It says if you have those things, then it guarantees you an absolute max or min. Your graph can look super weird like this one does, and you can still get an absolute max and an absolute min that way. Okay, one last thing to take a look at in this section, and that is mountain ranges. No, not really. But this is going to bring me to our last topic, which is local, also known as relative extreme values. We'll come back to those in a little bit. I do want to talk about mountain ranges. So normally I ask this question every year, have any of my students ever climbed a mountain? And a surprising number of students have over the years, which is a little bit terrifying. But let's say we're looking at a mountain range. We're just looking, we're not climbing, okay? And so we're going to make some mountains here, okay? I'm going to call this first one PP for Pigot Point. I'm going to call the peak, of course the peak, has to be HH, Higgins Hill. Yes, I know we're calling it a hill, but here we are. And then the little guy off to the side we'll call Mount Mantra. Okay, now I have no desire to climb a mountain, but if I climbed any of these mountains, I would be pretty happy, right? Even little Mount Mantra off to the side here, if I put a little flag on top of Mount Mantra, I would be pretty happy with that. So we'll do that. We'll get a little flag going here. We'll get the old stars and stripes up there. If I could do that, that would be pretty impressive. Okay. Is Mount Mantra the highest peak? Nope. Higgins Hill and Pigot Point are still looking down at little old Mount Mantra. But the way I like to think about it is that every peak is still a peak. It doesn't have to be the highest peak. And that's the idea behind a local or a relative extreme value. Okay, is that it doesn't have to be the highest point, it just has to be a high point. Okay, and so if we kind of apply this idea to this function here, right, we see a few things that are labeled maxes and mins. Okay, let's start with this one at x equals c. Okay, at x equals c, this is an example of what we call a local maximum. Okay, no greater value of the function nearby, right? It is still the peak of its own little mountain. Is it the highest peak? No, but it's still a peak. The highest one is an absolute maximum. That one is over to the right here at x equals d. So I will highlight this in green again, just like all my other absolute maximums. That right there is the highest peak, okay? And I'm also going to add on here that an absolute maximum is also a local maximum. Okay, right? The highest peak is still the top of its own mountain, right? Looking at the points just around it, right, it's still the highest point, not even, throughout the entire domain here, but just of the points around it. So every absolute maximum is also a local maximum, but not every local max is the absolute. Mount Mantra is a peak, but it's still not as high as Higgins Hill. Okay, we can also apply this to minimums as well. Right? In the middle of the graph here, right? I kind of think about minimums as like valleys, peaks and valleys. Okay, so what's the lowest valley here, right? This is not the lowest valley here at x equals e, right? But it's still a valley. Okay, so that is a local minimum. Over to the right, see how the graph kind of slopes down there and it ends? Right? Even though there's no graph to the right of it, right? Wherever the graph ends off at is also going to be a local minimum. And then also where it kind of starts off at, right? This is the lowest point on the graph. So this is an absolute minimum, but it's also going to be a local minimum. I'll write that above here. Okay, so all 5 of the highlighted points here are all local, also known as relative extreme values. Okay, but there is still only one absolute max and one absolute min. There is still the highest point in the whole mountain range and the lowest point in all of the valleys, right? But every peak of its own mountain, right, and every valley, the bottom of it, is its own high and low. And that brings me to the last idea here, which is let's talk about endpoints, okay? Because this graph started and ended, right, on 2 points here at x equals a and x equals b. And an endpoint is always going to be at least a local max or a local min. I don't like that O, so I'm going to change it. There we go. An endpoint is always going to be at least a local max or a local min. So at x equals a and at x equals b, right? If you have any sort of endpoint, it's always going to be a local. And in the case of x equals a here, it also happened to be the absolute minimum. Okay, so that does it for section 4.1 day 1, and I will see you next time.